All right, we're looking now at finding the area between two curves. So have a look at these three examples that we have here. First of all, this one here on the left. If we're wanting to find the area between the curve of f of x and the curve of g of x, remember that when we're finding the definite integral between two particular x values, say between a and b, for a particular curve, so for f of x, for example, that will give you the total area beneath the curve and up until we get to the x-axis. Okay. If we do the same thing for g of x, then that will give us this green shaded area that we see here. So if we're wanting to find the area between f of x and g of x, between the two x coordinates a and b, then we need to subtract the definite integral for g of x between a and b from the definite integral of f of x from a to b. We subtract those two areas, that will leave us with just this red or purple region, if you like, maroon region here between them. So it's the definite integral of f of x minus the definite integral of g of x will give you the area between the two curves. Now that's going to be the same for this next one as well. Even though it's below the x-axis, it's what we need to think of is it's whatever is higher, whatever is above, whichever function is above, that is the one that goes first, and we subtract the lower function from the higher function. So if we think through it, finding the definite integral from a to b of f of x will give you this green shaded region here. Okay. However, because they're below the x-axis, it will give you a negative value. Okay. So if we find the definite integral of g of x from a to b, that also will be a negative value, but it'll be this whole region here. So it'll be a bigger negative value than the one for f of x. But because they are negative, when we subtract the definite integral of g of x from the definite integral of f of x, you'll end up with a positive value equating or equal to this region between the two curves. Okay, and that will be the case also for this one here. So even though it crosses the x-axis, we're going to go definite integral of f of x minus definite integral of g of x from a through to b. And that's what's shown here. Okay, in each of these cases, f of x is the upper function, the higher function. G of x is the lower function. And so to find the areas between the curves, we can either do them as two separate integrals from a to b of f of x minus the definite integral from a to b of g of x, or you can put them as a single integral and then put f of x minus g of x in here, which allows us to simplify the expression as well. You can do that, and that will work. Okay, then you've got this other possibility that if we are finding the area between two curves and the curves intersect, and we're wanting to find the definite integral, or wanting to find the area between those two curves, and it spans across a region where they intersect and beyond, then we need to split the integral up. So what's important is that we can find these intersection points to get the related x coordinates that we can work with. So if we look then at this integral, or set of integrals that we need to calculate, from a to c1 with g of x minus f of x, g of x is this higher function, and so it's g of x minus f of x being the lower function for this region here, or between x equals a and x equals c1. Then we work out the definite integral from c1 to c2, but this time f of x is the higher function and g of x is the lower function, so it's f of x minus g of x, and then it swaps back again, g of x being the higher function, f of x being the lower function, so it's g of x minus f of x from c2 to b. So that is the principle involved in finding the area between two curves. Okay, and so we can look at this example that we have here. We want to find the area of the shaded region shown here. So we can see here our upper graph or function is 2x minus 1, the line, and the lower one is y equals x. So our area A will be the definite integral from 0 to 2. Those are our x values that we need to use, and it would be the definite integral of 2x plus 1 minus x with respect to x. Okay, so then what we can do here is simplify this expression, so that becomes 2x minus x, which is x plus 1, and then we can go through a straightforward process of integrating this, and so that gives us x squared over 2 plus x from 0 to 2. Substitute our 2 in first, so that becomes 2 squared over 2 plus 2 minus, we substitute 0, that's all going to become 0. So we're left with 4 over 2 is 2 plus 2 is 4 square units. Okay, and that is our shaded area that we've got there. So because we are calculating the area, we do need to include those units. Okay. For this one here, finding the area bounded by the graphs of the functions y equals x and y equals x squared. Notice it just says bounded by the graphs. It doesn't give us any x values. So let's just see what that means if we sketch the graph. So let's do that here. Okay, don't need to have a super precise graph. Let's look. So y equals x squared as a first instance is our most kind of basic parabola. We can kind of sketch that reasonably neatly. Okay, a little bit wobbly there, but that's okay. And then y equals x. So if we go with y equals x, that is going to have a graph that kind of looks like that. Would have been helpful I drew a little bit bigger, but anyway, we're looking at this region between those two graphs, bounded by the graphs. So this here, bounded by the graphs, implies that they intersect, okay, and there'll be like an enclosed region between the graphs, and so that's what we're looking at here, this enclosed region there. So what we need to know is, where do they intersect? Now we could probably work out where these intersect at 0 here for sure, okay, the origin, and this point here, well, we can probably work that out pretty easily, right? But let's just go through a process which will help us with further questions. So what we do is they will intersect where these functions are equal to each other. So because they both are with y as the subject, we can let these expressions equal each other. So in other words, x squared equals x, okay, and then to solve this properly we need to bring our x over to the other side with the x squared to equal 0, and then factor it, so take out x, leaving us with x minus 1 equals 0. It's important to do it this way. We could just divide both sides by x and that'll cancel on the x's, that'll only give us one solution. We do it this way, we will get both solutions that we need. So now using the null factor law, that means that either x is equal to 0 or x equals 1. Okay, so that tells us that that's our other x value. So we can find our area here by finding the definite integral from 0 to 1 of, now our higher function is not the parabola, that goes underneath, doesn't it? So it is actually y equals x, so it's x minus x squared dx. Okay, integrating those, that gives us x squared over 2 minus x cubed over 3 from 0 to 1. Substituting our 1 in first, that is 1 squared over 2 minus 1 cubed over 3 minus 0, of course, when we substitute the 0 in, and so that's 1/2 minus 1/3 and if we subtract those, common denominator will be 6, so that becomes 3 here minus 2 over 6, which is 1/6 units squared. That is our shaded area. Okay, so this last example that we're working on is looking at finding the area between this hyperbola, y equals 4 over x, and the straight line graph y equals x, between x equals 1 and x equals 3. So let's do a quick sketch so that we know what we're working with. So hyperbola, we know, curves down here and up here. It's a positive hyperbola. So let's sketch that in there. And then we have y equals x passing through the origin and at that point. Okay, so what we want is we need to know what is this point of intersection. So we're going to let these two functions equal each other. So let 4 over x equal x, multiply both sides by x, so we've got 4 equals x squared, which means when we take the positive and negative square root, we'll have plus or minus 2. So the negative 2 would be where they intersect down the bottom here, and this here is our x value at 2. Now we're wanting to go from 1 to 3, so we can do this point here, so that's 1, and then 3 would be roughly here. So this is our area that we are looking at. Okay. So in order to find the area here, we're looking at two separate integrals, from 1 to 2 and then from 2 to 3, because the higher function changes as we go through that x value of 2. So our area A will be equal to the integral from 1 to 2. Now our higher function is our hyperbola, so that's 4 over x minus our lower function of x plus the integral from 2 to 3 of x minus 4 over x dx. Alright, so we're now going to integrate. So this one here becomes 4 times the natural log of x minus x squared over 2 from 1 to 2 plus this becomes then x squared over 2 minus 4 times the natural log of x, and this one is from 2 to 3. Substituting now, we'll have 4 times the natural log of 2 minus 2 squared is 4 over 2 is 2 minus, put in brackets, substitute the 1, 4 log 1 minus, and 1 becomes 1/2. And then adding onto that our result by substituting the 3 and then the 2. So put that in brackets, we'll end up with 9 over 2 minus 4 log 3. And then minus, substituting our 2, that becomes 4 over 2 is 2 minus 4 log 2. Okay, let's go from here. 4 log 2 minus 2. Now 4 log 1, the log of 1 is 0, so then we just minus negative 1/2, so that becomes plus 1/2. And then plus 9 over 2 minus 4 log 3 minus 2 plus 4 log 2. So we can combine things here. We've got 4 log 2 there plus 4 log 2, so that's 8 log 2 minus 4 log 3, mix that up, minus 4 log 3, and then here we have 1 half plus 9 over 2, that's 10 over 2, which is 5. 5 minus 2 is 3, minus 2 is 1, so that's plus 1 units squared. And that's that question.